Hello there, and welcome to the Scientist Sleepy. Have you ever looked up at the night sky, at the countless pinpricks of light, and felt a profound sense of wonder, tinged with a quiet, unsettling question? If the universe is so vast, so ancient, and so full of possibilities, why is it so silent? Tonight, we embark on an exploration into the heart of this mystery, delving into the fascinating phenomena and fundamental principles that shape the Fermi paradox, seeking to understand why, amidst this grand cosmic tapestry, we seem to be the only one speaking. Please settle in. Allow yourself to become comfortable, to find a position that feels truly peaceful. If this journey into the quiet wonder of the universe resonates with you, consider gently tapping the like button and subscribing to the Scientist Sleepy. This helps us continue to create these calming havens for your rest. And as we begin, I invite you to share in the comments below. What is one quiet wonder about the universe that always sparks your curiosity? Your thoughts, like the distant stars, add to our collective contemplation. Now, let us turn our attention to the profound silence of the cosmos. The vastness of the cosmos holds secrets, and we often wonder if we are alone. This fundamental question, whispered in the quiet hours of the night, is as old as our capacity for wonder. We gaze up at the stardusted canvas, a seemingly infinite expanse, and an echo arises within us. Are we a solitary spark in this immense darkness, or are we but one voice in a grand, cosmic choir? The sheer scale of the universe, a concept that strains the very limits of our comprehension, suggests that life in some form should be not only possible but probable. Consider the numbers. Billions of galaxies, each containing billions of stars, and around many of those stars we are now discovering orbit planets. The sheer statistical probability, when laid out in such staggering terms, makes the idea of Earth being the sole haven for life seem almost improbable. Yet, despite this overwhelming mathematical likelihood, a profound silence greets our inquiries. Our telescopes, our radio dishes, our relentless pursuit of knowledge, have so far returned no definitive answer, no undeniable signal of another thinking, feeling entity. This silence is not merely an absence of information. It is a presence, a palpable quietude that deepens the mystery and amplifies our curiosity. It invites us to consider the very nature of existence, the conditions that allow life to bloom and the potential pathways, or perhaps the unbreachable barriers, that separate us from any other potential inhabitants of this boundless cosmic ocean. The stars are not just distant suns. They are silent witnesses to a grand cosmic drama, and we, on this small blue planet, are left to ponder our unique, or perhaps not so unique, place within it. This silent expanse beckons us to explore the boundaries of possibility, to delve into the profound implications of our apparent solitude, and to embrace the quiet wonder that such a contemplation can bring. It is in this stillness, in this profound questioning, that we begin to understand the intricate tapestry of the universe and our own small, yet significant, thread within it. The universe, in its silent grandeur, holds within it the potential for infinite stories, and our own is but one chapter, waiting to be fully understood. And so, the silent stars above become a mirror, reflecting our deepest questions about our place in the grand, unwritten narrative of existence. The sheer scale of the universe suggests life should be abundant, yet we hear nothing. Consider for a moment the sheer, breathtaking immensity of the cosmos. Our home, Earth, is but a tiny speck, a pale blue dot suspended in the inky blackness. Our sun, a solitary star among hundreds of billions within our own Milky Way galaxy. And our galaxy, a swirling island of stars, is just one of an estimated 2 trillion galaxies that populate the observable universe. 2 trillion. Each of those galaxies, a vast collection of stars, many of which, we now know, host their own planetary systems. The numbers are so staggeringly large they begin to lose all intuitive meaning. If we were to assign a single grain of sand to represent each star in the observable universe, the entire Earth would be buried under a mountain of sand taller than Mount Everest. And this is just what we can see. The universe is likely far larger, stretching out beyond our current observational limits. Now let us apply a simple, yet profound probabilistic logic. If the conditions that led to life on Earth, the right chemical ingredients, the presence of liquid water, a stable energy source, and a suitable planetary environment, are not unique to our little corner of the cosmos, then life in some form should have arisen elsewhere. And not just once or twice, but countless times. Across this unfathomable expanse, across billions of years of cosmic history, there should have been ample opportunity for life to emerge, to evolve, and for some of those life forms to develop intelligence and advanced civilizations capable of communication or exploration. The sheer number of potential Earth-like planets, the abundance of the fundamental elements of life throughout the universe, and the vast stretches of time available, all seem to point towards a universe teeming with life. It is this very abundance of potential, this overwhelming statistical likelihood, that makes the profound silence we experience so deeply unsettling. We look up at the night sky, a tapestry of countless distant suns, and the question echoes. If life is so likely, if the universe is so vast, then where is everyone? Why this profound, deafening quiet? And so, in this grand cosmic theater, the silence itself becomes a profound statement, a reminder that our understanding of life's prevalence is perhaps as vast and as unknown as the universe itself. The absence of evidence for extraterrestrial civilizations is profoundly puzzling. The sheer, almost unimaginable scale of the observable universe is the first element that lends weight to this puzzle. We are situated within a galaxy, the Milky Way, which itself contains an estimated 100 billion to 400 billion stars. And this is but one galaxy among potentially 2 trillion galaxies in the observable universe. Imagine, if you can, that number. 2 trillion galaxies, each with billions upon billions of stars. If we were to assign even a minuscule fraction of these stars to host planets, and then an even tinier fraction of those planets to exist within habitable zones where liquid water could potentially flow, the numbers still become astronomically large. The Kepler Space Telescope, and later the TESS mission, have confirmed that exoplanets are not a rarity, but rather the norm. Most stars, it seems, have planets. And many of these planets are rocky, Earth-sized worlds orbiting within their star's Goldilocks zone. Given these statistics, the probability that life in some form has arisen elsewhere seems to many to be overwhelmingly high. Yet when we turn our instruments towards the heavens, when we listen to the cosmic background radiation, when we scan the radio spectrum for any hint of intelligent communication, we find silence. A profound, deafening silence. This absence of any detectable signal, any artifact, any clear indication of other advanced civilizations, is what lies at the heart of the Fermi paradox. It is not just a lack of evidence. It is a lack of evidence that seems to contradict our most basic probabilistic estimations. If life is so likely to arise, and if civilizations are likely to develop the capacity for interstellar communication or travel, then where are they? This silence is not merely an observation. It is a deeply unsettling question that challenges our understanding of our place in the cosmos. It forces us to confront the possibility that our assumptions about the prevalence of life, or the nature of intelligence, or the trajectory of technological development might be fundamentally flawed. The universe, in its grand theater of stars and galaxies, appears to be remarkably empty of any recognizable actors beyond our own species. This quietude, this apparent solitude on such a vast stage, is precisely what makes the puzzle so profound, so persistent, and so deeply thought-provoking for the curious mind. It whispers a question that echoes through the silent void. Are we truly alone, or is there something we are fundamentally misunderstanding about the universe and the life it might harbor? This silence, far from being empty, is pregnant with possibility, with mystery, and with a quiet sense of awe that can lead us to a deeper contemplation of existence itself. The quiet of the cosmos, in its vastness, reflects a profound mystery, a silent testament to the unknown, gently inviting us to ponder our unique place within its grand design. Our understanding of the universe's age and size contradicts the silence. Consider the sheer immensity of the cosmos, a tapestry woven from billions of galaxies, each containing billions of stars. Our own Milky Way galaxy alone is estimated to harbor between 100 and 400 billion stars, and this is just one of countless celestial islands in the observable universe. The universe itself is thought to be approximately 13.8 billion years old, a staggering expanse of time that dwarfs human history. Within this immense volume and over this vast timescale, the fundamental ingredients for life, as we understand them, carbon, hydrogen, oxygen, nitrogen, and other essential elements, have been forged in the hearts of stars and dispersed throughout the cosmos by supernova explosions. These elements are not unique to our solar system. They are found everywhere in nebulae, in the atmospheres of distant stars, and on the surfaces of countless exoplanets. The discovery of exoplanets, planets orbiting stars other than our Sun, has been a revolution in our understanding of the universe. We now know that planets are not rare occurrences but are, in fact, exceedingly common. Many stars, perhaps even most, are orbited by planetary systems. Of these exoplanets, a significant fraction reside within their star's habitable zone, often referred to as the Goldilocks zone, where temperatures are theoretically just right for liquid water to exist on the surface, a key ingredient for life as we know it. Some of these planets are even Earth-sized and rocky, further increasing the statistical likelihood that life could have arisen elsewhere. If we extrapolate these numbers, the probability of life emerging on at least one other planet becomes remarkably high. The universe has had an incredibly long time to experiment with the formation of life. Given the abundance of stars, the prevalence of planets, and the widespread distribution of life's essential building blocks, it seems almost statistically improbable that Earth is the only planet where life has taken hold. The silence we perceive, therefore, seems at odds with the vast cosmic laboratory that has been operating for billions of years, brimming with the potential for biological innovation. This discrepancy between the expected abundance of life and the observed lack of any definitive signals is the very essence of the Fermi paradox, a profound question that echoes in the quiet void. The cosmic clock has ticked for eons, its hands sweeping across a canvas of unimaginable scale, and yet the grand symphony of life remains unheard. The probability of life arising elsewhere seems high, given the universe's conditions. Consider the sheer immensity of the cosmos, a canvas so vast it stretches our comprehension. Within this boundless expanse, the fundamental ingredients for life, as we understand it, are not rare anomalies but rather ubiquitous components. The universe is awash in the very elements that form the bedrock of our existence: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are not exotic substances confined to our little corner of the galaxy. They are forged in the hearts of stars and scattered across interstellar space through supernova explosions, seeding nebulae that eventually coalesce into new star systems. Our own sun is a second or third generation star, meaning the elements that make up our planet, and indeed ourselves, have been through multiple stellar cycles, becoming increasingly enriched with heavier, more complex atoms. When we look at the night sky, we are not merely observing points of light. We are witnessing the raw materials of countless potential worlds. The vast majority of stars in our galaxy, and by extension in the observable universe, are orbited by planets. Thanks to revolutionary advancements in astronomy, particularly with missions like Kepler and TESS, we now know that exoplanets are not a cosmic rarity but a cosmic commonplace. Billions upon billions of planets populate our Milky Way alone, and the universe contains hundreds of billions of galaxies, each with its own retinue of celestial bodies. This staggering number of planets increases the statistical likelihood of conditions suitable for life to arise. Furthermore, the concept of habitability extends beyond simply having a planet. We are learning that the conditions necessary for life might be more diverse and resilient than we initially assumed. The discovery of extremophiles on Earth, organisms that thrive in environments we once thought utterly inhospitable, such as deep-sea hydrothermal vents, highly acidic waters, or even within radioactive waste, demonstrates the tenacity and adaptability of life. These terrestrial examples suggest that life might find ways to exist in a wider range of cosmic environments than our Earth-centric view might allow. The presence of liquid water, long considered the sine qua non of life, is now being explored in subsurface oceans on moons like Europa and Enceladus within our own solar system, indicating that water, and potentially life, could exist far from the direct warmth of a star. The chemical processes that led to the origin of life on Earth, known as abiogenesis, are a subject of intense scientific inquiry. While the exact sequence of events remains a profound mystery, the fundamental building blocks of life, amino acids, nucleotides, have been detected in meteorites and interstellar clouds, suggesting that these complex organic molecules can form spontaneously in space. This implies that the initial steps towards life might not be an improbable fluke unique to Earth, but rather a natural consequence of cosmic chemistry, a cosmic recipe that could be repeated across the universe. The sheer number of opportunities, the countless planets, the widespread organic molecules, the diverse potential habitats, paints a compelling picture where life's emergence elsewhere seems not just possible, but statistically probable. And so, the universe, in its silent grandeur, may be teeming with nascent possibilities, a cosmic garden where the seeds of life have been sown across an immeasurable expanse. The Drake equation attempts to quantify the number of detectable civilizations. In our quest to understand the silence, to grapple with the profound question of whether we are alone, our minds often turn to the sheer probability of life's existence beyond our pale blue dot. It is a question that has echoed through human history, amplified by our growing knowledge of the cosmos. And in the mid-20th century, As our scientific understanding began to blossom, a remarkable attempt was made to bring a measure of order to this vast uncertainty. This attempt, a framework for thinking about the prevalence of extraterrestrial civilizations, is known as the Drake equation. It is not a definitive answer, but rather a sophisticated tool, a series of guiding lights, designed to help us ponder the factors that might lead to the emergence of detectable intelligent life in our galaxy. Conceived by Dr. Frank Drake in 1961, this equation is a probabilistic argument, a way to break down an overwhelmingly large question into a series of more manageable, albeit still challenging, components. It was born from a desire to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Imagine it as a cosmic detective's checklist, each item on the list representing a crucial step in the journey from the formation of a star system to the development of a civilization capable of sending signals across the interstellar void. The equation itself is elegantly simple in its structure, a product of several variables, each representing a different aspect of this complex cosmic puzzle. Let's explore these variables, not as dry numbers, but as stages in a universal unfolding. The first factor, often denoted as R*, represents the average rate of star formation in our galaxy. Our galaxy, the Milky Way, is a dynamic place, constantly birthing new stars from vast clouds of gas and dust. Understanding this rate helps us grasp the sheer number of potential homes for life that are being created over cosmic timescales. Following this, we consider Fp, the fraction of those stars that have planetary systems. For a long time, we assumed planets were rare, but recent astronomical discoveries have shown us that planetary systems are, in fact, incredibly common, with most stars likely hosting at least one planet. This is a profoundly encouraging step. Then comes Ne, the average number of planets that can potentially support life per star that has planets. This factor hones in on those crucial, habitable zones, regions around a star where conditions might be just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The next variable, Fl, is the fraction of those potentially habitable planets on which life actually arises. This is where the true mystery of abiogenesis, the origin of life from non-living matter, comes into play. It's a step that remains one of the most significant unknowns in our understanding of life's prevalence. If life arises, then we consider Fi, the fraction of planets with life on which that life evolves intelligence. This is another monumental leap, moving from simple microbial existence to beings capable of complex thought and problem-solving. Following this, we must account for Fc, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, such as radio transmissions. This is where the detectable aspect of the equation becomes critical. It's not just about life, but about life that can communicate with us across the vastness. Finally, the last variable, L, represents the length of time for which such civilizations release detectable signals into space. This factor is perhaps the most speculative, encompassing the lifespan of a technological civilization, whether it be a few thousand years or many millions. The Drake equation, therefore, is a beautiful, albeit incomplete, framework that guides our thoughts about the potential abundance of life in the universe, acknowledging that many of its components are still subjects of active scientific inquiry and philosophical debate. It reminds us that the universe is a place of immense possibility, and our search for answers is a journey of continuous discovery, each variable a stepping stone on the path to cosmic understanding. And so, with each factor considered, the Drake equation invites us to contemplate not just the numbers, but the intricate tapestry of cosmic evolution, a grand narrative woven from star birth, planetary formation, the spark of life, the ascent of intelligence, and the enduring quest for connection across the silent expanse. The mediocrity principle suggests Earth and its life are not unique. This principle, often a cornerstone of scientific reasoning, posits that there is nothing inherently special or exceptional about our planet, our star, or our place in the universe. It's a philosophical stance that encourages humility and broadens our perspective, suggesting that what we observe here on Earth is likely to be replicated elsewhere, given the sheer scale of the cosmos. Imagine a universe not as a grand stage for a singular, unique performance, but as an infinitely repeating play with countless actors and countless stages, all performing variations of the same fundamental themes. When we look at the Sun, a G-type main sequence star, we see that it is remarkably ordinary. It's not the largest, not the smallest, not the hottest, not the coolest. It's a perfectly average star in a galaxy brimming with billions of others, many of which are also G-type stars. This ordinariness extends to our solar system. We have rocky planets in the inner orbits and gas giants in the outer, a configuration that appears to be quite common among planetary systems. The chemical ingredients for life, as we know it, are also not rare. Spectroscopic analysis of distant stars and nebulae reveals the presence of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, the very elements that form the backbone of organic molecules. These elements are forged in the hearts of stars and dispersed throughout the galaxy by supernova explosions, seeding new star systems with the raw materials for life. Furthermore, the discovery of exoplanets has revolutionized our understanding of planetary prevalence. We now know that planets are not an anomaly. They are the norm. Billions of planets orbit stars in our own Milky Way galaxy, and many of these are situated within the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. If the conditions for life are so widespread, and the building blocks are so common, then the emergence of life itself, in its simplest forms, might also be a common occurrence. The mediocrity principle, therefore, doesn't just suggest that other planets are like ours. It suggests that the processes that led to life here could have unfolded countless times across the universe. It nudges us to consider that our existence, while miraculous to us, might be a statistically probable outcome of universal laws and conditions. This perspective can be both humbling and profoundly comforting, as it implies that we are not isolated observers in a cosmic void, but rather part of a grand, universal tapestry of existence, woven with the same threads that brought us into being. The universe, in its vast, indifferent embrace, likely contains echoes of our own story, playing out on countless distant stages. And so, the universe hums with the quiet potential for countless beginnings, mirroring our own in its grand, unassuming way. The Great Filter might explain why advanced civilizations are so rare. Imagine the immense journey from the very first spark of life to a civilization capable of traversing the stars. This path is not a gentle, linear ascent, but rather a series of monumental hurdles, each one a potential roadblock, a cosmic sieve that filters out the vast majority of aspiring life forms. This concept, often referred to as the Great Filter, is a theoretical explanation for the profound silence we observe in the universe, a silence that starkly contrasts with the immense number of potentially life-supporting planets. The Great Filter suggests that somewhere along this evolutionary and technological trajectory, there lies at least one step that is extraordinarily difficult, perhaps even nearly impossible to overcome. This filter could be behind us, meaning that the emergence of life itself, or the transition from simple single-celled organisms to complex multicellular life, or even the development of intelligence, was an incredibly rare event. If the filter is behind us, then humanity is exceptionally fortunate, having successfully navigated a nearly impassable barrier. Alternatively, the Great Filter could lie ahead of us. This is a more sobering thought, implying that the greatest challenge for any civilization, including our own, is yet to come. This future filter might manifest as a technological singularity that inevitably leads to self-destruction, a cosmic catastrophe such as a gamma ray burst that wipes out advanced life, or perhaps an inherent limitation in our ability to sustain a complex, technologically advanced society over long time scales. The nature of this potential future filter is a subject of much speculation. It could be the inability to manage the consequences of advanced technology, such as artificial intelligence that escapes our control, or the development of weaponry capable of planetary annihilation. It might also be an environmental collapse, a consequence of unchecked industrialization and resource depletion that renders a planet uninhabitable for its most advanced inhabitants. The universe is ancient, and the opportunities for life to arise and evolve have been numerous. If even a tiny fraction of these opportunities led to intelligent, technological civilizations, we should expect to see evidence of them. The absence of such evidence, the profound quiet, is what makes the Great Filter such a compelling, albeit disquieting, explanation. It forces us to consider our place in the cosmic narrative not as one among many, but perhaps as one of the very few, or even the only, to have successfully passed through its stringent, invisible gates. The implications are profound. If the filter is behind us, we carry the weight of an extraordinary cosmic accident. If it is ahead, we face a future that demands unprecedented wisdom and caution. The Great Filter is a humbling reminder that the universe's quiet might be a testament to the extreme rarity of reaching the stars, a cosmic whisper of the immense challenges life must overcome to simply exist, let alone thrive. The Fermi paradox asks where all the aliens are. This is the central question, the profound silence that echoes through the cosmos, a question born from the stark contrast between the sheer immensity of the universe and the apparent absence of any other intelligent life. When we look up at the night sky, a canvas dusted with billions upon billions of stars, each a distant sun potentially orbited by its own planetary system, it seems almost inevitable that life, perhaps even intelligent life, should have arisen elsewhere. The universe is ancient, over 13 billion years old, providing ample time for evolution to unfold across countless worlds. Our own galaxy, the Milky Way, contains an estimated 100 to 400 billion stars, and there are hundreds of billions of galaxies in the observable universe. If even a tiny fraction of these stars host planets, and a tiny fraction of those planets are suitable for life, and a tiny fraction of that life evolves intelligence, then statistically, the universe should be teeming with civilizations. Yet we have found no definitive evidence, no signals, no artifacts, no unmistakable signs of extraterrestrial intelligence. This profound silence, this lack of observable alien presence, is what Enrico Fermi famously pondered, leading to the paradox that bears his name. It's a paradox that challenges our assumptions, forces us to reevaluate our place in the cosmos, and encourages a deep introspection about the nature of life, intelligence, and the universe itself. Are we truly alone, a singular spark of consciousness in an otherwise barren expanse? Or are there other intelligences out there, perhaps so advanced or so different that we simply cannot perceive them? Or are they deliberately concealing themselves from us? The Fermi paradox isn't just an astronomical puzzle. It's a philosophical quandary that touches upon our deepest hopes and fears about existence, a silent question posed by the universe itself, waiting for an answer that may forever elude us. This silence, this cosmic quietude, is itself a profound phenomenon, one that compels us to explore the possibilities, to question our understanding, and to continue our search with a mixture of awe and deep, contemplative wonder. The universe, in its vastness, presents us with this enigma, a cosmic riddle that whispers of possibilities both wondrous and perhaps a little unsettling, reminding us of the profound mystery that surrounds our very existence. The silence itself becomes a voice, a subtle yet persistent inquiry into the nature of life and our solitary place within the grand cosmic tapestry. The universe, in its staggering immensity, presents a compelling argument for the widespread existence of life. Consider the sheer number of stars, each a potential sun, and the rapidly growing catalog of exoplanets, worlds orbiting those stars. It's estimated that there are more planets in our galaxy alone than there are grains of sand on all the beaches of Earth. Many of these exoplanets reside within their star's habitable zone, the region where temperatures might allow for liquid water to exist on the surface, a crucial ingredient for life as we know it. The building blocks of life, organic molecules like amino acids, have been detected in meteorites, comets, and interstellar gas clouds, suggesting that the raw materials are not unique to Earth but are ubiquitous throughout the cosmos. Furthermore, life on Earth arose relatively early in our planet's history, soon after conditions became stable enough to support it. This suggests that abiogenesis, the process by which life arises from non-living matter, might not be an exceptionally rare event, but rather a natural consequence of the right chemical and physical conditions. If life can arise readily, and if the universe offers countless opportunities for it to do so, then it seems logical to expect that many of these instances would eventually lead to the evolution of intelligent, technologically advanced civilizations, capable of communicating across interstellar distances. The Drake equation, a probabilistic argument formulated by Frank Drake, attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Even with conservative estimates for each of its factors, the rate of star formation, the fraction of stars with planets, the number of planets that can support life, the fraction of those that develop life, the fraction of life that develops intelligent life, the fraction of civilizations that develop technology that releases detectable signals into space, and the length of time such civilizations release signals. The equation often yields a number greater than 1, implying that we should not be alone. The paradox arises when we compare these seemingly high probabilities with the complete lack of any observational evidence. No confirmed radio signals, no alien spacecraft, no megastructures around distant stars. This stark discrepancy between expectation and observation is the heart of the Fermi paradox, a profound question that lingers in the quiet expanse between the stars. It forces us to confront the possibility that our understanding of life's prevalence, or our assumptions about how civilizations might behave or communicate, could be fundamentally flawed. The silence is not just an absence of sound. It is an absence of expected company, a cosmic void that begs for an explanation, a puzzle that continues to fuel our scientific curiosity and philosophical contemplation. The universe, in its vast silence, poses a question that echoes through our very being. Where are they? This profound absence, this quietude where we expect a symphony of cosmic voices, is the essence of the Fermi paradox, a gentle nudge from the cosmos itself, asking us to consider the extraordinary implications of our apparent solitude, reminding us that even in the grandest of narratives, the most humbling perspectives can be found in the quietest of moments. The concept of abiogenesis, the origin of life from non-living matter, is key. Abiogenesis, the genesis of life from non-living chemical components, stands as one of the most profound and fundamental questions in science, and a cornerstone in understanding the Fermi paradox. For life to arise and flourish elsewhere in the universe, the initial spark, the transition from inert matter to a self-replicating entity, must be a process that can occur under suitable conditions. This isn't about evolution, which describes how life changes and diversifies once it exists, but about the very first step, how life began. Scientists hypothesize that on early Earth, under conditions vastly different from today, with a different atmospheric composition, abundant energy sources like lightning and volcanic activity, and the presence of essential chemical elements, the simple inorganic molecules could have undergone a series of complex chemical reactions. These reactions, driven by energy, would have gradually led to the formation of more complex organic molecules, the building blocks of life as we know it: amino acids, nucleotides, and lipids. Think of it as a cosmic chemistry set, where the right ingredients and the right environment allow for the spontaneous assembly of incredibly intricate structures. These molecules, over vast stretches of time, may have organized into self-replicating structures, perhaps enclosed within primitive membranes, forming the very first protocells. This process is not a single miraculous event, but a gradual, step-by-step chemical evolution. The Miller-Urey experiment in the 1950s famously demonstrated that amino acids, the building blocks of proteins, could be synthesized from inorganic compounds under simulated early Earth conditions. While this experiment provided crucial evidence, it's just one piece of a much larger puzzle. The question of whether this process is a rare fluke or a common cosmic occurrence is central to the Fermi paradox. If abiogenesis is a highly probable event, occurring readily whenever and wherever the right conditions are met, then the universe should be teeming with life, and the silence becomes even more perplexing. Conversely, if abiogenesis is an extraordinarily rare event, requiring a precise and unlikely confluence of factors, then the rarity of life, and thus the silence, becomes more understandable. Understanding the precise pathways and probabilities of abiogenesis is therefore vital. It involves exploring how simple organic molecules assemble into complex polymers like proteins and nucleic acids, how these polymers gain the ability to self-replicate, and how they become enclosed within a boundary, separating them from their environment and allowing for the development of internal chemistry. Scientists are investigating various hypotheses, including the RNA world hypothesis, which suggests that RNA, a molecule capable of both storing genetic information and catalyzing chemical reactions, played a central role before DNA and proteins became dominant. Other theories explore the possibility of life originating near hydrothermal vents on the ocean floor, where chemical gradients and mineral catalysts could have provided the necessary conditions. The challenge lies in recreating these ancient conditions in the lab and observing the spontaneous emergence of self-replicating systems. It's a quest to understand not just life on Earth, but the potential for life across the cosmos, by unraveling the very first whispers of existence from the silence of the primordial. The journey from inert chemistry to the first living cell is a testament to the universe's capacity for complexity, a fundamental step that, if repeatable, suggests life's potential ubiquity, and if not, highlights its precious rarity. The universe, in its grand unfolding, has the potential to weave the tapestry of life from the simplest threads of chemistry, a silent testament to the profound possibility that existence itself can arise from the quiet interactions of matter and energy. The chemical building blocks for life are widespread throughout the cosmos. Consider for a moment the fundamental components that give rise to life as we know it. These aren't unique to our pale blue dot, but rather are scattered like stardust across the vast expanse. The universe, in its grand cosmic crucible, has forged the very elements that make biological processes possible. The most prevalent atoms, hydrogen and helium, are the primordial ingredients born in the Big Bang itself. But it's in the fiery hearts of stars, through the process of nucleosynthesis, that the heavier, more complex elements are created. Carbon, the backbone of all organic molecules; oxygen, essential for respiration; nitrogen, a key component of amino acids and DNA; and phosphorus, vital for energy transfer and genetic material. These are not rare curiosities. They are forged in stellar furnaces and then, through the majestic, violent explosions of supernovae, are dispersed across interstellar space. These elements coalesce into gas clouds, nebulae, which in turn become the birthplaces of new stars and planetary systems. So, the very atoms that form our bodies, that enable our thoughts, that allow us to ponder our existence, are not exclusive to Earth. They are ancient, cosmic travelers, present in the dust that forms distant planets, in the atmospheres of alien worlds, and in the interstellar medium that separates galaxies. This cosmic inheritance means that the potential for life, the raw materials for its emergence, are not limited to our solar system, but are a fundamental characteristic of the universe itself. Every atom in your being has a story that stretches back to the dawn of time and across unimaginable distances. And so, the very dust of distant stars whispers the potential for life, reminding us that our essence is woven into the fabric of the cosmos. Exoplanet discoveries reveal billions of potentially habitable worlds. Our understanding of the cosmos has expanded dramatically in recent decades, thanks to the relentless curiosity of scientists and the ingenuity of our technology. We once looked up at the night sky and could only speculate about worlds beyond our own solar system. Now, we have empirical evidence, and the numbers are staggering. The Kepler Space Telescope, for instance, and subsequent missions like TESS, have revolutionized our ability to detect planets orbiting other stars. These are exoplanets, and the sheer abundance we are finding suggests that our own solar system is not a cosmic anomaly, but rather a common occurrence. The data indicates that planets are not rare. They are, in fact, ubiquitous. For every star in our galaxy, it's estimated there are at least one, and likely many more planets. Considering there are hundreds of billions of stars in the Milky Way alone, This translates to trillions of planets within our galaxy. And our galaxy is just one of hundreds of billions, perhaps even trillions, of galaxies in the observable universe. This means the total number of planets across the cosmos is an almost incomprehensible figure, a number so large it dwarfs our everyday comprehension. But it's not just the sheer quantity that ignites our wonder, it's the potential for habitability. Scientists are not just finding planets, they are identifying those that reside within the habitable zone of their stars. This is often referred to as the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist on the surface. Liquid water is considered by many to be a fundamental prerequisite for life as we know it. These exoplanets come in a variety of sizes and compositions, from gas giants far larger than Jupiter to rocky, terrestrial worlds that might be similar in size to Earth. Some of these Earth-like planets are orbiting stars that are smaller and cooler than our Sun, like red dwarfs, which are the most common type of star in the galaxy. While red dwarfs present their own challenges, such as intense stellar flares, the sheer number of them, and the planets they host, makes them significant targets in the search for life. The ongoing analysis of exoplanet atmospheres, using advanced spectrographic techniques, is beginning to reveal clues about their composition, offering tantalizing hints about the presence of gases that could indicate biological activity. Each new discovery, each new data point, paints a picture of a universe teeming with possibilities, a cosmic ocean filled with countless islands, each holding the potential for its own unique story of existence. And so, in the quiet hum of distant suns, a billion potential cradles of life softly spin, reminding us that the universe breathes with possibilities, each one a whispered invitation to wonder. The Goldilocks zone, where liquid water can exist, is a crucial factor. The search for life beyond Earth is, at its heart, a quest for water. Not just any water, but liquid water, the universal solvent that facilitates the complex chemical reactions necessary for life, as we know it to arise and persist. This critical environmental condition is so fundamental that astrobiologists often refer to the region around a star where such conditions might prevail as the Goldilocks zone, or more formally, the circumstellar habitable zone. It's a concept that draws its name from the classic fairy tale, where Goldilocks seeks a porridge that is just right, not too hot, not too cold, but perfectly warm. Similarly, planets orbiting a star must be at a distance that allows for surface temperatures conducive to liquid water. Too close to the star, and any water would evaporate into space, leaving a parched and sterile world. Too far away, and the water would freeze solid, locking away its potential for life in an icy embrace. The precise boundaries of this zone are not fixed. They depend on the type and size of the star. Cooler, dimmer stars have smaller, closer habitable zones, while hotter, brighter stars have larger, more distant ones. Even the atmosphere of a planet plays a vital role. A thick atmosphere can trap heat, extending the habitable zone outwards, while a thin atmosphere might allow heat to escape, shrinking it. This delicate balance of stellar radiation and atmospheric insulation creates a narrow, yet potentially vast, cosmic neighborhood where the conditions for life might be met. When we discover exoplanets residing within these Goldilocks zones, they immediately become prime candidates for further investigation, igniting our curiosity and fueling our hope that we are not alone in this immense and wondrous universe. The implications are profound. If liquid water is the key, and if such zones are indeed common, then the universe could be teeming with worlds where life has had the opportunity to take root and flourish, perhaps in ways we can only begin to imagine. This cosmic sweet spot, where the temperature is just right, is a beacon of possibility in the silent expanse. And so, the delicate dance of distance and atmosphere creates pockets of potential, where the very essence of life, liquid water, might flow. The transition from simple, single-celled organisms to complex, multicellular life represents a profound evolutionary leap, a hurdle so significant that its rarity might be a primary factor in the cosmic silence. Imagine the early Earth, teeming with microbial life, a vibrant, albeit microscopic, ecosystem. For billions of years, this was the extent of life's complexity. These single-celled entities, like bacteria and archaea, were masters of their domain, incredibly resilient and adaptable, colonizing every conceivable niche. But the jump to multicellularity, the formation of organisms with specialized cells working in concert, was not a guaranteed outcome. It required a series of complex, interconnected evolutionary innovations. One of the most crucial was the development of mechanisms for cells to adhere to one another, to form stable communities. Following this, cells needed to learn to communicate with each other, to coordinate their activities, and to differentiate into specialized roles, some becoming structural, others metabolic, others reproductive. This differentiation is the very essence of complexity. Think of the vast differences between a single bacterium and a human being, or even a simple multicellular alga. The genetic and regulatory machinery required for this specialization is immense. Furthermore, the energy requirements for maintaining such complex structures are far greater than for single-celled life. This necessitates more efficient metabolic pathways and often a more substantial energy source. The evolution of eukaryotic cells themselves, with their membrane-bound organelles like mitochondria and nuclei, was a prerequisite for much of this complexity, a symbiosis between different prokaryotic cells that took place perhaps once, or very rarely, in the history of life. Even after the advent of eukaryotes, the path to multicellularity was fraught with challenges. The transition from simple colonies of identical cells to true tissues and organs, with intricate developmental programs and sophisticated intercellular signaling, is a monumental evolutionary achievement. It involves the precise regulation of gene expression over time and across different parts of the developing organism. This is not a simple, linear progression. It involves a delicate balance of cooperation and competition between cells, and the development of mechanisms to prevent uncontrolled growth, such as cancer. Consider the sheer improbability of these events occurring in sequence. Each step, from the initial formation of stable cell-to-cell adhesion to the development of complex organ systems and reproductive strategies, represents a branching point where life could have stalled or taken a different, less complex path. If this transition to complexity is indeed a rare event, requiring a specific confluence of genetic predispositions, environmental conditions, and evolutionary pressures, then it would naturally explain why the universe, while potentially brimming with microbial life, might be largely devoid of advanced, detectable civilizations. The universe could be a vast, silent ocean of single-celled organisms, with only a few scattered islands of complex life, making the chances of two such islands developing advanced technology and a means of interstellar communication exceedingly slim. The emergence of complex life is not merely a step. It is a series of improbable evolutionary cascades, a testament to the intricate dance of life's potential and the unforgiving nature of chance. The universe, in its quietude, might be whispering the profound rarity of life's intricate unfolding. Intelligence, as we understand it, might be an evolutionary fluke. Consider the immense tapestry of life that has graced our planet throughout its billions of years. From the simplest single-celled organisms that first emerged in the primordial oceans, to the staggering diversity of flora and fauna that populate our lands and seas today, evolution has sculpted countless forms, each exquisitely adapted to its niche. Yet among this vast biological panorama, the emergence of human-level intelligence, characterized by abstract thought, complex language, tool-making, and self-awareness, stands out as a remarkably rare phenomenon. Is this sophisticated cognitive ability a predictable outcome of evolutionary pressures, a kind of cosmic inevitability waiting to unfold wherever life takes root? Or is it, perhaps, something far more delicate and contingent, a fortunate confluence of specific environmental factors, genetic predispositions, and sheer chance, making it an extraordinary outlier rather than a universal rule? The path to human intelligence was not a straight line, but a winding, often circuitous journey marked by countless evolutionary dead ends and alternative strategies. For instance, consider the dinosaurs, which dominated Earth for over 160 million years. They developed complex social behaviors, diverse ecological roles, and impressive physical adaptations. Yet their cognitive evolution, as far as we can discern from the fossil record, did not lead to abstract reasoning or advanced technology. Similarly, many species exhibit remarkable problem-solving skills and sophisticated communication methods. The intricate dances of bees, the complex social structures of ants, the navigational prowess of whales, the tool use of crows and chimpanzees. These examples demonstrate that intelligence, in its various forms, is a valuable evolutionary asset, conferring significant survival and reproductive advantages. However, the specific constellation of traits that define human intelligence, our capacity for symbolic thought, for creating and manipulating abstract concepts, for building upon the knowledge of past generations through cumulative culture, and for contemplating our own existence and place in the universe, appears to be a far more elusive evolutionary prize. What were the precise pressures that favored such development in our lineage? Was it the need to navigate complex social hierarchies, the challenges of adapting to rapidly changing environments, the development of bipedalism freeing up our hands for tool use, or a combination of these and other factors? The evolutionary history of our hominin ancestors is a testament to this intricate interplay of pressures and adaptations. The development of larger brains, while conferring cognitive advantages, also came with significant costs, such as increased energy demands and difficulties during childbirth. For intelligence to arise and persist, these costs must have been outweighed by substantial benefits. Furthermore, the sheer timescale involved in evolutionary processes is staggering. Life has existed on Earth for approximately 3.8 billion years. The emergence of Homo sapiens and our distinct cognitive abilities is a comparatively recent event, occurring within the last few 100,000 years. This means that, for the vast majority of life's history on Earth, intelligent, technologically advanced civilizations, as we conceive of them, did not exist. This temporal perspective suggests that the evolutionary trajectory leading to our specific form of intelligence may have been exceptionally improbable. If we were to rewind the tape of life and play it again, would the outcome be the same? Would another form of intelligence emerge? Or would the evolutionary path diverge in countless other directions, leading to a universe populated by life forms that, while perhaps highly successful, do not share our particular brand of curiosity and capacity for abstract thought? The very definition of intelligence itself is a human construct, shaped by our own experiences and capabilities. It is entirely possible that other forms of intelligence exist or could evolve that are so fundamentally different from our own that we would not even recognize them. Perhaps intelligence is not a singular peak to be scaled, but a vast mountain range with myriad summits, each representing a different way of perceiving, interacting with, and understanding the universe. The possibility that our particular brand of intelligence is an evolutionary fluke, a fortunate accident of history, carries profound implications for our place in the cosmos. It suggests that the universe might be teeming with life, but not necessarily with beings who ponder the same questions or possess the same cognitive architecture as we do. The silence we perceive might not be an indication of cosmic emptiness, but rather a testament to the sheer diversity of evolutionary outcomes, where our own intelligence is a rare and precious blossom on the cosmic tree of life. This realization can foster a profound sense of humility and wonder, reminding us of the extraordinary circumstances that have led to our existence and our capacity to even ask the question of why we are here, and why the universe appears so quiet. This delicate dance of chance and necessity, which sculpted our minds, underscores the profound uniqueness of our own conscious experience in the silent expanse. Technological advancement to a level of interstellar communication is difficult. The journey from simple biological beginnings to a civilization capable of reaching across the vast cosmic ocean is not a linear, guaranteed progression. It involves a series of cascading challenges, each one a formidable barrier that could halt development indefinitely. Consider the very genesis of life. Even on Earth, a planet seemingly tailor-made for it, the transition from non-living chemistry to self-replicating entities was a process that took hundreds of millions of years, and we still don't fully understand its precise mechanisms. Once life emerged, the path to complexity was equally arduous. The evolution of multicellularity, of specialized tissues and organs, of nervous systems capable of processing information. These were not inevitable steps. Each involved a unique set of environmental pressures, genetic mutations, and a vast amount of time, punctuated by mass extinction events that reset the evolutionary clock. For a civilization to arise, it must not only achieve biological complexity but also develop intelligence. This intelligence must then be guided by a societal structure that values learning, innovation, and the pursuit of knowledge. The development of abstract thought, of language, of mathematics, of the scientific method, these are monumental intellectual leaps. And even with intelligence, the path to technology is fraught. Imagine the sheer luck and ingenuity required to discover fire, then to harness metallurgy, to understand electricity, to develop the principles of computation. Each of these breakthroughs required not only conceptual understanding, but also the availability of resources, the development of precise tools, and the transmission of knowledge across generations. Now, scale this up to interstellar communication. The energy requirements alone are staggering. To send a signal strong enough to be detected across light years, a civilization would need to master energy production on a scale far beyond what humanity currently comprehends, perhaps harnessing stellar energy or even manipulating spacetime itself. Furthermore, The technology for detecting such signals is equally sophisticated. It requires immense radio telescopes, or perhaps entirely different sensory apparatuses that we haven't even conceived of, all calibrated and maintained with incredible precision. The lifespan of such a technological phase is also a critical factor. Civilizations might reach a certain technological apex only to be undone by internal strife, environmental degradation, or the very technologies they develop. The development of nuclear weapons, of artificial intelligence that could become uncontrollable, of bioengineering gone awry. These are all potential self-inflicted wounds that could extinguish a nascent interstellar civilization before it ever had a chance to broadcast its presence. The sheer number of near misses and almosts in evolutionary and technological history suggests that reaching the threshold of interstellar communication is an exceptionally rare achievement, a delicate balance of countless favorable factors that might only align in a minuscule fraction of potential life-bearing worlds. It is a summit that few, if any, can ever hope to reach, a testament to the profound difficulty of the cosmic climb. The arduous climb to the stars, marked by countless evolutionary hurdles and technological chasms, underscores the precious fragility of any civilization that dares to whisper into the void. The lifespan of a technological civilization might be inherently short. Consider for a moment the arc of our own species, Homo sapiens. We have been the dominant intelligent species on Earth for a mere blink of an eye in geological time. Yet, within this incredibly brief span, we have rapidly developed technologies that have fundamentally altered our planet and begun to reach beyond it. This rapid ascent, while remarkable, also highlights a potential fragility. Technological advancement, particularly when it outpaces wisdom and foresight, can become a double-edged sword. Imagine a civilization that, like us, achieves the capacity for self-annihilation through nuclear weapons, engineered pandemics, or uncontrolled artificial intelligence, all within a few centuries of developing these capabilities. The sheer power unleashed by advanced technology can be so immense, so destructive, that a single catastrophic mistake, a moment of collective folly, could be enough to extinguish a civilization entirely. It is entirely plausible that the very technologies that allow a civilization to become detectable across the vastness of space, the powerful radio signals, the immense energy expenditures, are also the technologies that make its demise swift and absolute. Perhaps the window of opportunity for a civilization to exist in a state where it can transmit signals and be detected is a fleeting one, a brief, bright flash before it either succumbs to its own creations or achieves a level of maturity where such overt transmissions are no longer necessary or even desirable. The universe, in its immense patience, might simply be observing a cosmic lottery, where the prize of long-term survival is awarded only to those who can navigate the perilous journey from technological infancy to a stable, enduring existence. The silence we perceive could be the echo of countless civilizations that, in their haste to conquer the stars, stumbled and fell, their brief, brilliant light extinguished before it could ever truly reach us. And so, the ephemeral nature of technological existence may be a quiet testament to the delicate balance between innovation and preservation. The lifespan of a technological civilization may be inherently limited by its own actions. Consider the profound and sobering possibility that advanced civilizations, much like our own, might face an existential threat not from external cosmic forces, but from within. The very ingenuity that allows a species to develop sophisticated technologies, to comprehend the universe and manipulate their environment, could also be the source of their undoing. Imagine a civilization that has mastered the atom, capable of harnessing immense energy, yet also capable of unleashing unimaginable destruction. The history of our own planet, sadly, offers a stark and unsettling preview. We have witnessed the devastating power of organized conflict, the capacity for societies to inflict immense suffering upon themselves and their surroundings through warfare, often fueled by ideological differences, competition for resources, or sheer misunderstanding. The development of increasingly potent weaponry, from conventional explosives to nuclear arsenals, presents a clear and present danger, a constant tightrope walk between progress and annihilation. Beyond the specter of war, there is the insidious threat of environmental collapse. As a civilization expands its technological footprint, it inevitably interacts with and alters its planetary environment. The extraction of resources, the generation of waste, the alteration of atmospheric composition, these are all consequences of industrial and technological advancement. A civilization that fails to achieve a sustainable balance with its biosphere, that consumes its planet's life-sustaining capacity at an unsustainable rate, risks rendering its home world uninhabitable. This could manifest as runaway climate change, catastrophic loss of biodiversity, pollution of vital resources like air and water, or a combination of these factors, leading to a slow, agonizing decline rather than a sudden, explosive end. The interconnectedness of ecological systems means that a significant disruption in one area can have cascading, unforeseen consequences across the entire planet, a delicate web of life that, once torn, is incredibly difficult to mend. Furthermore, the very technologies that propel a civilization forward can also harbor unforeseen dangers. The rapid pace of technological development can outstrip a civilization's wisdom and foresight. Consider the potential for artificial intelligence to evolve beyond its creator's control, for advancements in genetic engineering to have unintended and catastrophic biological consequences, or for the mismanagement of complex, interconnected technological systems to lead to widespread, cascading failures. The pursuit of progress, without a commensurate development of ethical frameworks, risk assessment, and robust safety protocols, can inadvertently pave the path to self-destruction. A civilization might develop the means to achieve immortality, only to fall victim to a flaw in its own creation. It might unlock the secrets of faster-than-light travel, only to discover a fundamental paradox within its own technological framework. These are not mere science fiction fantasies. They are logical extensions of the challenges inherent in advanced technological development. The universe, in its immense silence, may be whispering a warning that the greatest barrier to interstellar longevity is not the vastness of space, but the fragility of the civilizations that inhabit it. The echoes of civilizations lost to their own progress may be the silent testament to the universe's quietude. Resource depletion could halt a civilization's progress. Consider the fundamental requirements for any developing civilization. At its core, progress, especially technological and societal advancement, is inextricably linked to the availability and management of resources. Think of the very foundations of our own civilization: energy, raw materials, fertile land, and clean water. These are not infinite. Every step forward, every innovation, every expansion has, until now, been fueled by tapping into the Earth's bounty. But the Earth's bounty, while vast, is not inexhaustible. As a civilization grows, its demands increase exponentially. The extraction of rare earth metals for electronics, the burning of fossil fuels for energy, the clearing of forests for agriculture and urban sprawl, these activities, while propelling us forward in the short term, inevitably lead to the depletion of finite reserves. Imagine a civilization on a finite world, much like our own planet. Their early stages might involve abundant, easily accessible resources. They might discover energy sources that are simple to harness, materials that are readily available. This allows for a period of rapid growth, innovation, and expansion. However, as their population increases and their technological sophistication grows, their consumption patterns intensify. They might exhaust the most easily mined ores, leaving only deeper, more difficult and energy-intensive deposits. The readily available fossil fuels might dwindle, forcing them to seek more complex and potentially dangerous alternatives. Their agricultural output, once supported by fertile topsoil, might decline as land becomes degraded or overused. Clean water sources, once plentiful, could become scarce and polluted. This isn't merely about running out of a single commodity. It's about a systemic decline. When the cost, in terms of energy and effort, to acquire essential resources becomes too high, it can stifle innovation. Why invest in developing new technologies when the fundamental building blocks are becoming prohibitively expensive or difficult to obtain? The economic and social strain of resource scarcity can lead to conflict, instability, and a shift in focus from progress and exploration to mere survival. A civilization might find itself trapped in a cycle of diminishing returns, where each attempt to solve a resource problem creates a new one, or requires more resources than it ultimately provides. This could lead to a plateau in their development, or even a gradual decline, where their ability to maintain their existing infrastructure and societal complexity begins to falter. They might possess advanced knowledge, but lack the material means to implement it on a grand scale. The very engines of progress, energy, materials, and a stable environment would be sputtering, leaving their grandest ambitions unrealized, their cosmic whispers silenced by the quiet hum of scarcity. Just as a candle burns brightest before it flickers out, a civilization's peak brilliance may be directly preceded by its most voracious consumption, a poignant reminder that even the most advanced journeys can be grounded by the very substance of the worlds they inhabit. The vast distances between stars present insurmountable travel challenges. Consider for a moment the sheer immensity of the space that separates even our nearest stellar neighbors. Proxima Centauri, the closest star to our Sun, is approximately 4.24 light-years away. A light-year, as we know, is the distance light travels in 1 year, and light, the fastest thing in the universe, journeys at a staggering 299,792 kilometers per second. To put that into perspective, if you were to travel at the speed of light, it would still take you over 4 years to reach Proxima Centauri. Now, imagine a spacecraft, even one capable of approaching a significant fraction of the speed of light. To reach Proxima Centauri at, say, 10% the speed of light would take 42.4 years. For the crew, this might be a lifetime or multiple generations. Our current propulsion technologies are minuscule in comparison. The Voyager 1 spacecraft, one of humanity's fastest probes, is traveling at about 17 kilometers per second. At this speed, it would take approximately 75,000 years to reach Proxima Centauri. This is not a journey for a single civilization's lifespan, nor even for a significant portion of its history. The energy requirements to accelerate a substantial vessel to even a fraction of light speed are astronomical, far beyond our current capabilities, and potentially beyond the physical limits imposed by the universe itself. Even if we could achieve relativistic speeds, the journey would still be measured in decades or centuries. Furthermore, the interstellar medium itself presents hazards. Even sparse dust particles, when encountered at near-light speeds, would have the kinetic energy of significant explosions, capable of destroying a spacecraft. Shielding against such impacts would require immense technological solutions. These are not merely engineering problems, they are fundamental physical constraints. The very fabric of spacetime, as described by Einstein's theories of relativity, suggests that exceeding the speed of light is impossible. While concepts like warp drives or wormholes remain in the realm of theoretical physics and science fiction, their practical realization is fraught with immense challenges, requiring exotic matter or energy densities that we have not yet observed or understood. The sheer scale of the cosmos, therefore, acts as a profound barrier. It suggests that even if civilizations are abundant, the practicalities of interstellar travel and communication might confine them to their own stellar neighborhoods. The vast, silent gulfs between stars are not just empty space. They are immense temporal and energetic hurdles, shaping the very possibility of cosmic connection. And so, the light years stretch out, a silent testament to the profound separation that nature imposes, reminding us that even the grandest journeys are often measured in the patient unfolding of time and immense, quiet distances. The speed of light, the ultimate cosmic speed limit, presents a profound barrier to galactic communication and travel. Imagine a universe so vast that even the most fundamental constant of physics, the speed at which light travels, becomes a measure of immense separation. This constant, approximately 299,792 kilometers per second, or about 186,282 miles per second, is not just a number. It is a fundamental property of spacetime itself. It dictates the very fabric of how information and matter can traverse the cosmos. For any civilization, no matter how advanced, to send a message or a probe to another star system, they are bound by this speed. Even if a civilization could achieve speeds approaching that of light, a journey to the nearest star system, Proxima Centauri, which is about 4.24 light-years away, would still take over 4 years. A light-year is the distance light travels in 1 year, a staggering distance in itself, approximately 9.46 trillion kilometers or 5.88 trillion miles. So, a message sent at light speed would take over 4 years to reach Proxima Centauri, and another 4 years for a reply to return, totaling a minimum of 8 years for even the most basic interstellar conversation. This temporal delay is not a mere inconvenience. It is a fundamental constraint that shapes the very possibility of a galactic community. Consider the sheer scale of our own Milky Way galaxy, which is estimated to be about 100,000 light-years in diameter. To send a signal from one side of our galaxy to the other would take 100,000 years. Even if we were to discover a civilization just a few thousand light-years away, a mere speck within our galactic neighborhood, a conversation would span millennia. This makes the idea of a bustling galactic network, where civilizations regularly exchange information and visit each other, incredibly difficult to reconcile with our understanding of physics. It implies that any extraterrestrial civilizations we might encounter are likely to be incredibly isolated, perhaps unaware of each other's existence, or existing in a state of profound temporal separation. The vastness of space, amplified by the immutability of the speed of light, creates an almost impenetrable barrier. It suggests that if advanced civilizations are out there, they are not just distant in space, but also distant in time from our own potential interactions. This limitation profoundly impacts our imagination of what a galactic society might look like. It is not a matter of building faster ships or more powerful transmitters. It is a fundamental aspect of the universe's architecture. The speed of light, therefore, serves as a cosmic quarantine, ensuring that even if life is common, meaningful interaction across the vast interstellar distances remains an extraordinary, perhaps even impossible, feat for most of cosmic history. This fundamental constraint shapes our perception of the universe, transforming it from a potentially crowded cosmic neighborhood into an expanse of profound, echoing solitude, where each civilization might be an island unto itself, separated by unimaginable gulfs of both space and time. The universe, in its grandest scale, whispers of isolation, bound by the unyielding pace of its fastest messenger. The possibility of civilizations existing in forms we cannot recognize is high. Our current definitions of life and intelligence are inherently anthropocentric, meaning they are based on our own human experience. We tend to imagine alien life as being carbon-based, requiring water, and perhaps even resembling us in some fundamental way. But the universe is a vast laboratory of possibilities, and life, in its myriad forms, could have evolved along entirely different paths. Consider the fundamental building blocks. While carbon is an excellent element for forming complex molecules due to its bonding capabilities, other elements might serve similar roles in vastly different biochemical systems. Silicon, for instance, is often discussed as a potential alternative, capable of forming long chains, though its chemistry is generally less versatile than carbon's in Earth-like conditions. But what if life doesn't even rely on chemistry as we know it? Could there be forms of existence based on energy fields, or perhaps on quantum phenomena that we are only beginning to grasp? We are, after all, still grappling with the fundamental nature of consciousness and existence, even within ourselves. To assume that extraterrestrial intelligence would manifest in a way that is immediately recognizable to us is a profound limitation of our own perspective. Imagine a civilization that communicates not through sound waves or electromagnetic radiation, but through subtle gravitational fluctuations, or by manipulating the very fabric of spacetime in ways that are imperceptible to our current instruments. Perhaps their existence is so intertwined with their environment that they are indistinguishable from it. Consider life that exists at scales far beyond our perception, either microscopic or macroscopic, or life that exists in environments we deem utterly inhospitable, like the interiors of stars or the crushing pressures of gas giants. Our search for extraterrestrial intelligence, or SETI, largely focuses on radio signals, a technology we developed relatively recently. It is entirely possible that advanced civilizations have long surpassed such methods, employing forms of communication or existence that are currently beyond our scientific imagination or technological capability to detect. Their intelligence might not be expressed through tools, cities, or even discernible biological forms as we understand them. It could be a collective consciousness, a distributed network, or a form of existence that operates on timescales so vast that their actions appear to us as mere cosmic background noise or natural geological processes. The universe is not obligated to conform to our expectations. It is far more creative and diverse than we can currently comprehend. This inherent unknowability of alien forms of life and intelligence is not a reason for despair, but a profound invitation to wonder and to expand our own understanding of what it means to be alive and to be intelligent. Our limited understanding of life's potential forms casts a vast shadow over our cosmic solitude, reminding us that the universe's greatest wonders may be those we are not yet equipped to perceive. Life might exist in subsurface oceans on icy moons. Beneath the frozen crusts of distant worlds, a hidden potential for life thrives, a concept that expands our very definition of where life can take root. For so long, our search for extraterrestrial life has been tethered to the familiar image of Earth-like planets, bathed in starlight, with liquid water on their surfaces. But the universe, in its boundless creativity, offers alternative cradles for existence. Consider the icy moons of our own solar system, like Europa, a moon of Jupiter, or Enceladus, a moon of Saturn. These celestial bodies, seemingly inhospitable from afar, possess a profound secret: vast oceans of liquid water hidden beneath kilometers of ice. The evidence for these subsurface oceans is compelling and has been gathered through sophisticated probes and observations. On Europa, for instance, the surface is crisscrossed with reddish-brown lines and cracks, suggesting a dynamic, shifting crust, which in turn points to a liquid layer beneath. Gravitational measurements and magnetic field data further support the existence of a salty, conductive ocean. The tidal forces exerted by their massive parent planets, Jupiter and Saturn respectively, act like a cosmic hand, constantly squeezing and stretching these moons. This gravitational kneading generates internal heat, enough to keep the water in a liquid state, even at such extreme distances from the sun. But water, while essential, is only one ingredient. The question then arises: what about energy and nutrients? Here, the icy moons offer surprising possibilities. Geysers of water vapor and ice particles erupt from Enceladus, sampled by the Cassini spacecraft, revealing a composition rich in salts, organic molecules, and even silica grains. These grains suggest hydrothermal activity at the seafloor, similar to the black smokers found on Earth's ocean floor. On Earth, these deep-sea hydrothermal vents teem with life, chemosynthetic bacteria forming the base of an entire ecosystem that thrives in perpetual darkness, independent of sunlight. If such vents exist on the seafloor of Europa or Enceladus, they could provide the necessary chemical energy and dissolved minerals to support microbial life, or perhaps even more complex organisms, hidden from our gaze. The implications of life arising and persisting in such environments are staggering. It would mean that life is not confined to the sunlit surfaces of planets, but can flourish in the cold, dark depths, powered by geological processes rather than stellar fusion. It suggests a universe far more hospitable to life than we might have initially imagined, with countless potential habitats hidden beneath frozen shells, waiting to be discovered. This possibility transforms the seemingly barren icy moons into potential oases of life, reminding us that the most extraordinary discoveries often lie where we least expect them, beneath the surface of the familiar. And so, the possibility of hidden oceans on distant moons whispers a profound truth. Life's tenacity finds expression in the most unexpected of places, painting a universe not of emptiness, but of quiet, submerged wonder. Extraterrestrial intelligence might not use radio waves for communication. Our current methods for searching for alien life, known as SETI, the search for extraterrestrial intelligence, are largely centered around listening for radio signals. This is a logical starting point, given that radio waves are a form of electromagnetic radiation that can travel vast distances through space, are relatively easy to generate and detect, and are a fundamental part of our own technological development. We've been using radio for over a century, and it allows us to broadcast information across our planet and even send probes out into the solar system. It's a natural assumption that any civilization capable of developing advanced technology would likely harness this same fundamental aspect of physics for interstellar communication. However, this assumption might be a significant limitation in our search. Imagine a civilization that developed millennia before us, or perhaps evolved along a completely different technological trajectory. They might have moved beyond radio waves as their primary means of long-distance communication long ago, perhaps to methods that are far more efficient, sophisticated, or simply beyond our current comprehension or detection capabilities. For instance, they might utilize directed energy beams, such as lasers, for communication. Lasers can be highly focused, allowing for more information to be transmitted with less energy dispersion, making them more efficient for interstellar point-to-point communication than omnidirectional radio broadcasts. While we do search for optical signals, our radio listening programs are far more extensive. Another possibility is the use of neutrinos, elusive subatomic particles that can pass through matter almost unimpeded. While incredibly difficult to generate and detect, a sufficiently advanced civilization might have mastered this technology, allowing for communication that is virtually undetectable by conventional means and unaffected by interstellar dust and gas. Furthermore, their technology might not even rely on electromagnetic radiation at all. Perhaps they have discovered ways to manipulate spacetime or utilize quantum entanglement for instantaneous communication across vast distances, a concept that, while theoretical for us, could be a fundamental aspect of their reality. It's also possible that their very definition of communication is different. Our understanding is based on transmitting information in a way that is decipherable. Perhaps advanced beings communicate through shared consciousness, or by subtly altering the fabric of reality in ways we are not equipped to perceive. To assume that alien civilizations would follow our technological path, particularly in communication, is a form of anthropocentrism. We are looking for echoes of ourselves in the cosmic silence, and in doing so, we might be missing entirely different symphonies of existence. The universe is vast and diverse, and the forms life and intelligence might take are likely as varied as the stars themselves. Focusing solely on radio waves, while a necessary starting point, may be akin to a single-celled organism trying to understand the entirety of human literature by only analyzing the vibrations of a drum. The universe might be broadcasting in a language we haven't yet learned to hear, using instruments we haven't yet conceived of. This realization doesn't diminish the importance of our current efforts, but rather expands our perspective, urging us to consider the boundless possibilities of what intelligence might look like, and how it might choose to speak across the unfathomable gulfs of space. It is a humbling reminder that our current understanding is but a single, small window onto an infinitely larger and more mysterious reality. The universe may be speaking in a language of light and shadow, of gravity's whisper and quantum's hum, a symphony far grander than our radio dials can capture. Perhaps they have already visited, but we haven't recognized the evidence. The sheer immensity of cosmic time and space offers a profound canvas for possibilities, and among the most intriguing is the notion that we might not be the first, nor the only, intelligent observers to have graced this corner of the galaxy. It is a thought that gently nudges at our anthropocentric view of existence, suggesting that the evidence of extraterrestrial visitation may be all around us, yet simply beyond our current capacity to perceive or interpret. We are, after all, a relatively young species in terms of our scientific understanding, and our methods of detection and interpretation are inherently limited by our own biological and technological frameworks. Imagine, for a moment, a civilization that mastered interstellar travel eons ago. Their journeys might have been so ancient, so far removed from our present, that any physical traces they left behind have long since been eroded by the relentless processes of cosmic erosion, geological change, or perhaps even transformed into something we now perceive as natural phenomena. Consider the possibility of visitors whose very existence is so fundamentally different from our own that their passage would leave no discernible mark upon our current understanding of science. They might not rely on the crude, energetic emissions of radio waves that we currently scan the heavens for. Their technology could be based on principles we haven't yet conceived of, or their physical forms might exist in dimensions or states of matter that are invisible to our current instruments. Perhaps their interactions with our planet were subtle, observational, or even ephemeral, leaving behind only the faintest whispers in the cosmic background, or encoded in ways that require a paradigm shift in our scientific thinking to decipher. We are like children playing on a beach, finding only the most obvious shells, while the true treasures of the ocean remain hidden in the deep, unseen currents. The vastness of time means that civilizations could rise and fall, leaving behind remnants that are either too subtle for our current detection methods or have been so thoroughly integrated into the natural processes of the universe that they are indistinguishable from the background. Think of the ancient mysteries on Earth itself, the unexplained megalithic structures, the enigmatic artifacts, the persistent myths and legends that hint at visitors from beyond. While science often seeks rational explanations within our current understanding, the possibility remains that some of these anomalies are indeed echoes of past encounters, misunderstood or misinterpreted by subsequent generations. It is also conceivable that their visits were not intended to be overt or intrusive. They may have observed us from a distance, like naturalists studying a particular ecosystem, leaving no footprint, no discernible interaction, simply gathering data and moving on. Or perhaps, their understanding of the universe is so advanced that they operate on principles of causality and interaction that are far beyond our current comprehension. They might be able to manipulate spacetime in ways that render their presence undetectable by our current means, or their very essence might be so alien that our sensory apparatus and scientific instruments are simply not equipped to register it. The universe is a library of unimaginable scope, and we have only just begun to learn to read its most basic alphabet. The evidence of visitation may not be in the form of crashed spacecraft or alien artifacts, but rather in the subtle patterns of cosmic evolution, in the very fabric of spacetime, or in phenomena that we currently dismiss as mere natural curiosities. To truly find such evidence, we might need to expand our definitions of what constitutes evidence and what constitutes life or intelligence itself. The universe is a symphony of countless notes, and we are only just beginning to discern the melody. And in this vast, silent expanse, the thought that we may have already been touched by other intelligences, however subtly, adds a profound layer to our quiet wonder. The zoo hypothesis suggests we are intentionally being observed. Imagine, if you will, a vast cosmic sanctuary, a grand preserve where nascent civilizations like our own are allowed to develop undisturbed, shielded from the more advanced, perhaps overwhelming, presence of interstellar societies. This is the essence of the zoo hypothesis, a compelling, if somewhat unsettling, answer to the Fermi paradox. It posits that the reason we haven't detected any alien signals or encountered extraterrestrial beings is not because they don't exist, but because they have made a deliberate choice to keep us in a state of isolation, much like a zookeeper might keep a rare species in a carefully managed enclosure, observing its natural behaviors without interference. This hypothesis suggests that advanced civilizations, having achieved a level of technological and ethical maturity, have established a galactic policy of non-interference with developing worlds. They might be observing our progress, our struggles, our triumphs with a detached curiosity, akin to how we might observe ants in a colony or wildlife in a national park. The implications are profound. It means we are not alone, but our solitude is a carefully constructed illusion, a protective bubble. The silence we perceive is not an emptiness, but a deliberate quietude, a space curated for our growth. This hypothesis doesn't necessarily imply malice or a lack of interest. Rather, it suggests a sophisticated understanding of development, perhaps a recognition that direct contact could be detrimental to a young civilization, disrupting its natural evolutionary trajectory, its cultural development, or even its very existence. Think of the potential chaos, the societal upheaval, the existential crisis that the sudden revelation of technologically superior beings could trigger on Earth. The zoo hypothesis offers a gentle, albeit paternalistic, explanation for this silence, framing it as an act of cosmic stewardship. It's a thought experiment that allows us to ponder our place in the universe not as isolated pioneers, but as inhabitants of a meticulously managed cosmic garden. The advanced beings, if they exist and adhere to this hypothesis, would possess the technology to remain unseen and unheard, masters of stealth and observation. They might monitor our radio transmissions, our energy signatures, our biological evolution, all from a safe, undetectable distance. They might even have protocols in place to prevent accidental detection, ensuring their presence remains a secret. This could explain why, despite our increasingly sophisticated telescopes and listening devices, we have found nothing. The universe in this scenario is not empty, but rather, it is filled with watchful, silent custodians. It's a concept that shifts our perspective from one of potential cosmic loneliness to one of being part of a larger, unseen, and perhaps benevolent galactic community, albeit one that has chosen to remain in the shadows for our own perceived good. The sheer scale of time and space also plays a role here. If there are civilizations that have existed for millions or billions of years longer than us, their understanding of ethics, of development, and of the universe itself would likely be far beyond our current comprehension. Their decision to observe rather than interact could stem from a deep wisdom, a recognition of the delicate balance of the cosmos. It allows us to continue our journey of discovery and self-determination, on our own terms, within the confines of our own planetary cradle, unaware of the eyes that might be watching, the minds that might be studying, the silent guardians of our cosmic infancy. The zoo hypothesis, therefore, is not just about aliens. It's about our own potential future, our own potential wisdom, and the vast, unknown ethical considerations that might govern a truly advanced interstellar society. It's a thought that can be both humbling and strangely comforting, suggesting that perhaps, in our apparent solitude, we are simply not yet ready for the universe to reveal its full, breathtaking scope. In this grand cosmic sanctuary, our perceived isolation is a gentle, deliberate embrace, a silent testament to a universe that watches and waits for our unfolding story. The dark forest theory posits that civilizations hide to avoid predation. Imagine, if you will, the universe not as a grand, welcoming neighborhood, but as a vast, silent, and perilous wilderness. This is the unsettling premise at the heart of the dark forest theory, a compelling, albeit chilling, potential answer to the Fermi paradox. It suggests that the reason we hear no alien signals, the reason the cosmos appears so empty, is not because life is rare, but because every intelligent civilization, driven by a primal instinct for survival, has learned to remain utterly silent. The theory, popularized by Liu Cixin in his science fiction novel, The Three-Body Problem, paints a stark picture. In this hypothetical dark forest, every civilization is an armed hunter, stalking through the trees, trying to remain undetected. To reveal oneself is to invite destruction. The logic is brutally simple. If you encounter another hunter, you cannot be certain of their intentions. Are they friendly? Are they curious? Or are they, like you, a predator in this cosmic jungle, looking for an easy meal or a competitor to eliminate? Given this profound uncertainty, the safest course of action, the only rational choice for long-term survival, is to eliminate any other life form you detect before it can eliminate you. Therefore, any civilization that develops the capacity for interstellar communication or travel faces an existential dilemma. To broadcast its existence is to announce its location to every other hunter in the forest. The risk is immense, the potential reward minimal. The very act of sending out signals, of searching for others, becomes an act of supreme vulnerability. It is akin to a lone camper in a dangerous forest shouting into the darkness, hoping for a friendly voice, but instead, potentially attracting the attention of a wolf pack. The theory proposes that the most successful, the most enduring civilizations are those that have mastered the art of invisibility, that have learned to suppress their curiosity about the wider universe, and that have dedicated their resources and intelligence not to outward exploration, but to maintaining their own secrecy and security. They would actively avoid any actions that might betray their presence, such as emitting powerful radio signals, engaging in large-scale interstellar engineering projects that could be detected, or even exploring too aggressively into unknown territories. The silence we perceive, then, is not an absence of life, but a deliberate, universal strategy of self-preservation. It is the sound of countless potential predators holding their breath, listening, waiting, and choosing to remain unseen. This theory suggests that the universe is not silent because it is empty, but because it is full of beings who are terrified, and rightly so, of being found. The implications are profound. It means that our own efforts to communicate with extraterrestrial intelligence, our hello to the cosmos, might be the most dangerous thing we have ever done. It shifts our perspective from one of hopeful discovery to one of cautious, perhaps even fearful, existence. We may be living in a universe where the loudest silence is the sound of intelligent life, desperately trying not to be heard. A silent testament to the ultimate price of existence in a potentially hostile cosmos. Within this vast, hushed expanse, survival dictates a profound, unwavering quietude. Interstellar colonization may be inherently impractical or undesirable. The dream of humanity spreading across the stars, of establishing new homes on distant worlds, is a powerful and enduring one. It speaks to our inherent drive for exploration, for survival, and for the continuation of our species beyond the confines of our single planet. However, when we subject this grand vision to the cold, hard scrutiny of scientific and practical realities, a different picture begins to emerge. The sheer scale of interstellar distances, for instance, presents a formidable, perhaps insurmountable barrier. Even traveling at speeds that are currently theoretical, reaching the nearest star system would take lifetimes, multiple lifetimes, for human crews. The energy requirements for such journeys are astronomical, far beyond anything we can currently conceive of generating or sustaining. Imagine the resources, the sheer material and energetic investment required to launch even a single vessel capable of carrying enough people and supplies to establish a self-sufficient colony. This isn't just about building a ship. It's about creating an entire self-contained ecosystem, a mobile world that can sustain life for centuries without resupply. And what of the destination? We might find a planet that appears Earth-like from afar, only to discover it harbors subtle, yet lethal, environmental differences. Perhaps the atmospheric composition is toxic in ways we can't detect with current technology, or the local microbial life is aggressively pathogenic to our biology. The genetic diversity of a founding population would also be a critical concern. A small, isolated group, susceptible to genetic drift and inbreeding, could face severe health challenges over generations, making long-term survival precarious. Furthermore, the psychological toll of such an undertaking cannot be overstated. Generations born and raised on a spaceship, with no memory of Earth, no concept of a natural sky or a vast, open landscape, would be fundamentally different beings. The very definition of humanity might begin to shift. Beyond the sheer practicality, there's also the question of desirability. Would we, as a species, truly benefit from such an endeavor, or would it be an act of desperation, a flight from problems we've created on Earth rather than a genuine step forward? The immense resources and ingenuity required for interstellar colonization might be far better spent on preserving and improving our home world, on solving the very issues that might drive us to seek refuge elsewhere. The romantic ideal of spreading across the galaxy might, in reality, be a logistical nightmare and a profound existential gamble, a quest that drains the very lifeblood of humanity for a highly uncertain and potentially bleak outcome. It's a humbling thought that perhaps our destiny, for all its cosmic potential, is bound more closely to our origins than we might wish to admit. And so, the grand exodus to the stars, while a beautiful aspiration, may remain a whisper in the cosmic night, a dream too vast and too costly to ever truly awaken. The universe might be intentionally sterile to protect nascent life. Consider, for a moment, a profound and perhaps unsettling thought. What if the apparent emptiness of the cosmos is not a consequence of chance, but a deliberate design? This is the essence of the cosmic nursery hypothesis, a fascinating, albeit speculative idea that suggests the universe might be intentionally kept quiet and relatively unpopulated, at least in its more accessible regions, to provide a safe environment for life to emerge and evolve without premature interference. It's a concept that flips the Fermi paradox on its head, moving from the question of where are they to why aren't they here, or even more radically, are they being kept away? The core of this hypothesis rests on the idea that a highly advanced, wise, and ethically developed civilization, or perhaps a collective of such civilizations, might understand the inherent dangers of unchecked expansion and contact. Imagine a scenario where the cosmos is viewed not as a frontier to be conquered, but as a delicate garden to be tended. In this view, the emergence of life, particularly intelligent life capable of self-awareness and complex societal structures, is a rare and precious event. The universe, in its early stages, is a chaotic place, filled with cosmic hazards like gamma-ray bursts, asteroid impacts, and the raw, untamed forces of stellar evolution. For life to have a genuine chance to take root and blossom, it needs a period of relative peace and stability. This intentional sterility could manifest in several ways, though we must acknowledge these are currently beyond our direct observational capabilities and reside firmly in the realm of philosophical conjecture and theoretical extrapolation. One possibility is that advanced civilizations possess technologies that actively suppress or deter the emergence of other, less developed civilizations until they reach a certain level of maturity. This isn't necessarily a malicious act, but rather a form of cosmic guardianship, akin to how we might protect a fragile seedling from being trampled. They might understand that premature contact with a more advanced species could be devastating, either through accidental disruption, cultural contamination, or even deliberate exploitation. By maintaining a vast, seemingly empty space, they create a buffer zone, allowing nascent life to develop along its own trajectory, free from external pressures that could lead to its premature demise or distortion. Another interpretation of this intentional sterility involves the concept of cosmic ethics or galactic stewardship. If a civilization has achieved a level of technological and philosophical advancement where it can survey the universe and understand the delicate balance of life, it might actively work to prevent the spread of potentially destructive forces. This could involve subtle interventions, perhaps guiding the evolution of stars or nebulae in ways that create more stable environments for life, or conversely, subtly discouraging the development of technologies that could lead to rapid, uncontrolled expansion and potential conflict. The vast distances themselves, while a natural barrier, could be seen as a deliberately maintained one, ensuring that civilizations develop in isolation, fostering unique forms of life and culture, and learning to overcome their own challenges without the disruptive influence of others. Furthermore, this hypothesis touches upon the idea that the universe might be a vast experiment, a series of carefully curated environments where life is allowed to emerge and evolve under specific conditions. The silence we perceive, the lack of readily detectable signals, could be the result of a universe that is actively managed to prevent the premature arrival of competing or incompatible life forms. This could be to protect the integrity of the evolutionary process, allowing each unique spark of life to reach its full potential without being extinguished by a more dominant presence. The universe, in this view, is not so much empty as it is carefully managed, a cosmic sanctuary where life can slowly and deliberately find its way. This concept also resonates with the idea of great filters, but places the agency for these filters outside of natural evolutionary processes and within the domain of intelligent, intentional action. It suggests that the reasons for the silence are not necessarily inherent limitations of life or technology, but rather deliberate choices made by those who have already navigated the perilous journey of cosmic adolescence. The quiet is not an accident. It is a consequence of wisdom, a testament to a profound understanding of the fragility and preciousness of life in the grand cosmic tapestry. It is a universe that waits patiently for life to be ready, for life to be wise enough to join a silent, perhaps benevolent cosmic community. And in this vast, intentionally quiet expanse, life can slowly unfurl, a delicate bloom in a cosmic garden, protected from the harsh winds of premature encounters. Our current search methods might be fundamentally flawed. The universe is a canvas of unimaginable scale, and our attempts to find other life are in many ways akin to a single, tiny hand reaching out into an infinite ocean, hoping to grasp a specific, perhaps non-existent seashell. For decades, our primary method of listening for extraterrestrial intelligence has been through radio astronomy, specifically the search for extraterrestrial intelligence, or SETI. We point our sensitive telescopes towards the stars, listening for narrowband radio signals that would stand out against the natural cosmic background noise. This approach is based on the assumption that advanced civilizations would use radio waves for communication, much like we did for a significant portion of our own technological development. However, this is a very human-centric assumption. What if other civilizations evolved to use entirely different methods of communication? Perhaps they communicate through neutrino bursts, gravitational waves, or even forms of energy transmission that we haven't yet discovered or can't even conceive of. Our technology, while impressive, is still in its infancy compared to the potential ages of other civilizations. Imagine a civilization that has been around for millions or even billions of years. Their technology would likely be so advanced that our current understanding of physics might be laughably primitive to them. They might have moved beyond the need for bulky radio transmitters, or perhaps they communicate instantaneously across vast distances through methods that defy our current comprehension of space-time. Furthermore, our search is often limited to specific frequencies, assuming that other civilizations would choose the same, quiet, parts of the radio spectrum to avoid interference. But this is a gamble. They might choose frequencies we haven't thought to monitor, or their signals might be so powerful and pervasive that they would be indistinguishable from natural phenomena to our current instruments. We are also limited by our own technological capabilities and the sheer cost and effort involved in searching such a vast volume of space. We can only monitor a tiny fraction of the stars and a limited range of frequencies. It's possible that other civilizations are out there, broadcasting their existence, but their signals are simply too faint, too brief, or too alien for us to detect with our current tools and methodologies. The possibility that our search is looking in the wrong place, with the wrong tools, or for the wrong kind of signal is a humbling, yet crucial, consideration in understanding the silence. We are, in essence, trying to find a needle in a cosmic haystack, but we might not even know what the needle looks like, or that the haystack is far larger and more complex than we can currently perceive. This limitation in our search strategies is a significant part of the Fermi paradox. It's not just that they aren't here, but perhaps we are simply not equipped to find them, even if they are. Our limited tools and assumptions might be the very walls that keep the cosmic conversation from reaching our ears. Our calm exploration has covered the profound silence of the universe, a silence that echoes with the Fermi paradox. We have delved into the staggering probabilities that suggest life should be everywhere, yet we find ourselves seemingly alone. We've considered the vastness of space and time, the intricate dance of chemistry and physics that allows life to emerge, and the potential cosmic hurdles that might prevent civilizations from reaching a point of detectable existence. We've touched upon the idea that perhaps life takes forms we cannot yet comprehend, or that civilizations choose paths that render them invisible to our current methods of detection. The possibility of self-destruction, the sheer immensity of interstellar distances, or even deliberate non-interference from more advanced beings all offer intriguing, albeit somber, perspectives. This quiet wonder, this grand mystery, invites us to contemplate our own place in the cosmos with a renewed sense of awe and a gentler perspective on our solitary existence. For now, the universe, in its quiet majesty, offers us a profound lesson in humility and curiosity. It reminds us that even in the absence of answers, the pursuit of understanding is a journey of immense value. It encourages us to look up at the stars not with anxiety, but with a peaceful, contemplative wonder, recognizing that the unknown is as much a part of our existence as the known. Sleep well, good night. It is time to rest now. If you happen to still be awake, you can drift into the next chapter now.